Good morning, my dear friends. Today, our topic that we are going to discuss is about principal components analysis. What is principal components analysis? It is nothing but an exploratory technique used to reduce the dimensionality of the data set to 2D or 3D. The principal components analysis can be used to reduce number of dimensions in data. It also can be used to find patterns in high dimensional data. It is also used to visualize data of high dimensionality. Example applications are face recognition, image compression, gene expression analysis. Principal components analysis ideas. What is the main idea behind the principal components analysis? Does the dataset span the whole of d-dimensional space? For a matrix of m samples by n genes, create a new covariance matrix of size n by n. Transform some large number of variables into a smaller number of uncorrelated variables that are called as principal components. It is developed to capture as much of the variation in data as possible. If you can see, we can represent the principal component analysis by this axis. Here you can see we have x1, y1, x2, y2 like this. Here y1 is the first eigenvector, y2 is the second eigenvector, y2 is ignorable. You can see what is the key observation that you can see here, how the data are distributed along y1, x1 plane and y1, x2 plane and coming to y2. Principal component analysis, we need to first understand one attribute first. For example, we need to pose a question, how much spread is in the data along the axis? That means how much distance to the mean. For example, variance, we can calculate the variance as standard deviation, okay, into 2. Here, what is the S square? That is nothing but variance. The formula for calculating the variance is sigma I equal to 1 to n xi minus x bar whole square. Here x bar represents the difference. So what is the difference between xi and x bar? That need to be summed and squared divided by n minus 1. For example, you can take the one attribute we considered here is temperature. We have different temperatures like 42, 40, 24, 30, 15, 18, 15, 30, 15, 30, etc. Now consider two dimensions. Now along with temperature we here consider humidity also, y-axis. So covariance, it measures the correlation between x and y. Covariance is mainly used to measure the correlation between x and y, how the x and y are related with each other. So for example, you can see covariance of xy. If the correlation between x and y is equal to 0, then we can say that they are independent. If you observe the covariance of xy is greater than 0, that means move in the same direction. If the covariance of xy is less than 0, then move in the opposite direction. So how can we give the formula? Covariance of xy is equal to sigma I is equal to 1 to n xi minus x bar into yi minus y bar divided by n minus 1. Here we have taken the sample data for temperature and humidity. More than two attributes, how to calculate? If there are more than two attributes, covariance matrix will be applicable. Contains covariance values between all possible dimensions. Here dimensions are nothing but attributes. Now when you come across more than two attributes, we are going to have a covariance matrix that can be given by C of nxn equal to Cij by Cij equal to covariance of dimension I comma dimension j. Let us take an example for three attributes x, y, z. How do you compute? For example, there are three attributes. C is equal to covariance of x comma x, covariance x comma y, covariance x comma j. Coming to y attribute, covariance of y comma x, y comma y, covariance of y comma z. So covariance of z comma x, z comma y, covariance of z comma z, three attributes. Eigenvalues and eigenvectors. Vectors x having same direction as Ax are called eigenvectors of A. Here A is an n by n matrix. In the equation Ax equal to lambda x, lambda is called an eigenvalue of A. Here we can see the example for this. You can we have taken the 2 by 2 matrix 2 3 2 1 into x 3 2, that is 2 by 1. Here we are going to get 12y, that is nothing but 4x of 3 2. Here 4 is called the eigenvector. So here we are going to, in the equation Ax equal to lambda x, here lambda is called an eigenvalue of A. So Ax equal to lambda x, that implies A minus lambda I of x is equal to 0. How to calculate the x and lambda values? First you need to calculate the determinant of A minus lambda I, which yields a polynomial that is of degree n. Determine roots to determinant of A minus lambda I equal to 0. Roots are here nothing but eigenvalues lambda. Solve A minus lambda I of x equal to 0 for each lambda to obtain eigenvectors x. Principal components. What are the principal components we have? Principal component PC1, the eigenvalue with the largest absolute value, will indicate that the data have the largest variance along its eigenvector, the direction along which there is greatest variation. Next, principal component 2, the direction with maximum variation left in data orthogonal to the first PC, first principal component. In general, only few directions are managed that are used to capture most of the variability in the attributes. So how do you calculate the steps of PCA? First, let x bar be the mean vector taking the mean of all rows. Adjust the original data by the mean, that is the variation, that is x minus x bar. Compute the covariance matrix C of adjusted x. Find the eigenvectors and eigenvalues of C. So for matrix C, vector E is nothing but column vector having same direction as C. Eigenvectors of C is E such that C equal to lambda I. Lambda is called an eigenvalue of C. Here C equal to lambda I, that implies C minus lambda I of E is equal to 0. Most data mining packages are going to use this. Eigenvalues. Calculate eigenvalues lambda and eigenvectors x for covariance matrix. Eigenvalues lambda j are used for calculation of what is the variation, that is percentage of total variance Vj for each component j. Vj equal to 100 into lambda j by sigma x equal to 1 to n lambda x. Sigma x equal to 1 to n lambda x equal to n. Here we can observe the principal components PC1, PC2, PC3, PC4, PC5, PC6, PC7, PC8, PC9, PC10 in x-axis and variance in percentage in the y-axis. We can see the PC1 is somewhere between 20 to 25. PC2 is between 15 to 20, PC3 is between 10 to 15, PC4 5 to 10, PC5 0 to 5, PC6, PC7, PC8 like that. So transformed data, eigenvalues lambda j corresponds to variance on each component j. Thus we need to sort by lambda j. Take the first p eigenvectors Ea, where p is the number of top eigenvalues. These are the directions with the largest variances. yi1, yi2, so on up to yip. We take that equal to e1, e2, so on ep. xi1 minus x1 bar, xi2 minus x2 bar, so on xin minus xn bar. Here, if you take an example, we have x1, x2 values. Similarly, x1 bar, x2 bar values. So here we are going to take an example with the mean 1. When you calculate the mean 1, for x1 values 24.1 we get. For x2, the mean calculated is represented by mean 2, that equal to 53.8. In the series 1, we can observe how the variance of the representation is done. Covariance matrix, nothing but C is equal to 75, 106, 10648. Using MATLAB, we find out eigenvectors. That is E1 equal to minus 0.98, minus 0.21, lambda 1 equal to 51.8, E2 equal to 0.21, minus 0.98, lambda 2 equal to 560. Thus, the second eigenvector is more important. If we only keep one dimension, that is E2, we keep the dimension of E2 equal to 0.21, comma, minus 0.98. We can obtain the final data as yi equal to 0.21 minus 0.98. That is xi1, xi2 equal to 0.21 into xi1 minus 0.98. Here we can observe the data and data adjust, how they are represented in the representation of graph. Here mean adjusted data with eigenvectors overlaid. Here we can observe how this data is being transferred, distributed. Now the covariance adjusted values that are represented from the scale 0 to 2 in this direction, and this one is 0 to minus 2. This portion represents the positive, the variations, where the data is represented in this form. Okay, PCA data adjust data, that is how much the values that we are going to get. Here a transformed data, that is equal to x and y. Here we have a double values. Okay, what is the PCA relationship between PCA and original data? Retrieving old data, example in data compression. So retrieved raw data equal to raw feature vectors transformed into final data plus original mean, yields original data using the chosen components. Principal components, general about principal components are summary variables, linear combinations of the original variables, uncorrelated with each other, capture as much of the original variance as possible. Applications of PCA are, the first one is gene expression analysis. What is the purpose of this? Determine core set of conditions for useful gene comparison. What are the dimensions, conditions, observations, genes? Yeast sporulation dataset consists of 7 conditions, 6118 genes. Result is 2 components capture most of variability, that is 90%. Issues: uneven data intervals, data dependencies. PCA is common prior to clustering. Crisp clustering question: genes may correlate here with the multiple clusters. Alternative is determination of genes clauses. So if you see the two-way angle data analysis, how the gene expression, first we are going to consider samples of 10 power 1 to 10 square. that will be given to the next gene expression matrix. Here we can see the genes of 10 cube to 10 power 4 are also there. The conditions here, the genes 10 cube to 10 power 4, they are applied with the conditions 10 to 10 square gene expression matrix. PCA example, here we can see how it is represented. PC1 is taken in x-axis and PC2 is taken along the y-axis. PCA on all genes, leukemia data, precursor B and T. Here plot of 34 patients have been considered. Dimensions of 8973 genes reduced to 2. PCA on 100 top significant genes, leukemia data, precursor B and T, plot of 34 patients, dimension of 100 genes here reduced to 2. Here we can see the PCA of genes, how they are arranged here. Here they can observe the plot of 8973 genes. We have taken the dimension of 34 patients reduced to 2. See how they are distributed.